So as of now, 16 students have joined. So let's wait 2 more minutes and after that we will start. Okay. So good evening, everyone. My name is Amit Kumar Sharma, and I welcome you all to this NPTEL live session for the course Hydrogen Energy, Production, Storage, Transportation and Safety. The course instructor is Professor Pratibha Sharma from IIT Bombay, and I am this course TA. So as you all know that every week there will be some recorded session uh, on the NPTEL course, and every week on Friday 6 to 8 p.m. we will have a live session. So in this session we will discuss the previous week brief summary and we will solve some previous year's assignment questions so that you will understand how to approach the assignment question and you will have a brief idea about the question and their patterns. So this meeting is being recorded, okay, and the PPT that I'm using here will be shared with you and also this recording will be shared to you. So NPTEL team will provide a Google Drive link. So on that particular link, you will find the PPT and video both. So don't worry about this. And if you have any query regarding any assignment questions, you can email me or we can discuss in our live sessions. So like, as you know that week 1 is already completed, so that in this class, we can discuss week 1 all questions. Okay, if you have any query, so like in a particular week, if you have a query, just email me prior to the class so that we can discuss in the class. Never ask any question regarding your next week. Okay, so we are in week 1, so this session will be only for week 1. So don't ask any doubt, any query regarding week 2 course content. Okay, so first we can start with a brief introduction. So I am pursuing my PhD at IIT Delhi and I am this course TA. So I am working on biogas fed solid oxide fuel cell. So basically I'm also working in modeling and hydrogen part. So that's why I'm taking this course. And let's start with your introduction. So just explain your little background, your name, and what is the motivation to join this course. Okay, somebody is unmuted. Please mute yourself. Nikhil, you are unmuted. Please mute yourself. Thank you. Okay, so start from Abhijanan Metra. Just quickly introduce yourself and what is your motivation to join this course?
Hello, sir. Myself, Abhigyan Mitra. Currently, I am doing PhD in Indian Institute of Petroleum and Energy, Actually, because of this course, I want to study the hydrogen energy because my subject is photocatalytic hydrogen generation. So this course helped me a lot about hydrogen production and know better than the hydrogen production.
Okay, thank you. Next, Anil Kumar.
Hello. Hello.
Yeah, hi. Yeah, hello.
Hi, sir. Myself Anil Kumar Manu. I'm working in Godrej Agarwal Limited, and
Okay, your
I
voice
want to
is not
improve my knowledge.
clear. Please check your mic actually. Yeah. Anil, your voice is not clear.
Now audible, sir?
Yeah,
Hello.
now it's okay. Yeah, you can all call me Amit only. It's okay. Yeah.
Yeah. Amit sir, this is Anil Kumar Manu working in Godrej Agarwal Limited. Uh,
Mm-hmm.
Actually, I'm very much interested in this course. Uh, in future, it will help. Hello.
Yeah, okay,
Hello.
okay. I think your voice is still not clear.
Yeah,
Okay,
yeah. Some
maybe
network
we
issue.
can come to you later actually. Yeah, I think some network issues there.
Yeah.
Okay.
Okay.
Okay, thank you. Next, Arpit Singh.
Yes, sir. A
Yeah,
very good
just
evening, sir.
yeah.
My name is Arpit Singh.
Good
Currently,
evening.
I am pursuing BTech degree from IIT Lucknow, first year. My branch is chemical engineering. So this topic is related to my branch. So I am here for the getting an overview about the topic.
Okay, thank you. Nice. Nikhil Sampath.
Hello, sir. My name is Nikhil Sampath. I am currently pursuing BTech Chemical Engineering in Shastra University. I have opted this course as an honors. Thank you.
Thank you. Bipin Kushwaha.
Hi Amit, this is Bipin Kushwaha. I am a chemical engineer and rightly pursuing my apprenticeship in BPCL. With the rising
Okay.
demand of hydrogen energy and clean energy, I am pursuing this course so that I can make my career in hydrogen field. This is my motivation.
Hmm, nice. Thank you. Chandrasekhar Prasad.
Good evening all. I hope I'm audible, right?
Good evening. Yeah, you are audible. Yeah, you are audible.
Right.
Yeah, please.
Probably I may be the oldest person here in this group. I have been in the auto industry for last 27 years, and,
Oh, nice.
incidentally, I've always been in engine and emissions and performance also. And as a curiosity, I'm just trying to see, and hydrogen has been one of my dreams also to see. Incidentally, I'm doing my PhD also in the green hydrogen, so that's made me to join this.
Okay. And from where you are doing your PhD?
And VTU, Shiveshwaraya Technical University, Government of Karnataka.
Okay. Nice, nice. Thank you.
Yeah.
Harsh.
Good evening, everyone. Am I audible?
Yeah, you are audible. Yeah.
I am Harsh Chauhan. I am pursuing chemical engineering from IIT Lucknow, and I am doing this course as my summer course.
Okay. Thank you. Thank you. Hari Krishnan AP.
Good
Okay.
evening, everyone. This is Hari Krishna. I'm
Good
currently
evening.
pursuing BTech Chemical Engineering at Anna University from Tamil Nadu. The reason why I choose the hydrogen production and energy is we are moving towards the more renewable.
I think there is some issue with your mic or network.
Hello.
Yeah, now you are audible. Yeah.
So can you hear me?
Yeah, now you are audible.
So
Now you are
myself, Hari
audible.
Krishna, currently pursuing
Mhm.
BTech Chemical Engineering. Yeah, okay.
Okay. Yeah. Okay.
Chemical
Thank you.
Engineering from Anna University from Tamil Nadu. The
Mm-hmm.
reason why I chose hydrogen energy is because we are. So I like to know more about the hydrogen fuels.
Okay. Okay. Thank you. Thank you. Jayaprakash. Okay. Jayendran Venkateshan.
Yes, I'm Jayendran Venkatesan. I'm basically mechanical engineering, and I have been with a company called Flowserve, who manufacture valves for oil and gas industry. So, as an emerging trend, I see that hydrogen is also going to be used in the valve industry. So that's the interest.
Okay. Okay, nice. Uh, Kali Selvan G.
Yes, sir.
Yeah.
Sir, I am
Just a
doing
little bit introduction. Yeah. Yeah. Yeah.
I'm doing second year EEE in Nehru Institute of Engineering and Technology. I am little eager to know about hydrogen energy production and about it, sir.
Okay. Okay. Thank you. Kiran Kumar.
Hello, am I audible?
Yeah. Yeah.
Hello.
You're audible. Yeah. Yeah.
Yeah. This is Kiran Kumar. I'm basically a chemical engineer. I'm working in Rashtriya Ispat Nigam Limited as a manager operations. So I want to look ahead for my career in hydrogen energy. So I'm have taken this course. That's it.
Okay. Thank you. Dheeraj.
Hi, myself Dheeraj Kolge. I have been working in oil and gas industry for past 10 years as an instrumentation engineer, and I can see I see the upsurge of in demand for green hydrogen products in our company as well. They're offering one product, so I'm keen to learn more about it.
Nice. Thank you. Manish. Okay. Manoj Kumar. Okay. Nitesh Shah.
Hello,
Yeah.
Manoj Kumar here.
Yeah.
Amit,
Yeah.
am I
Yeah.
audible?
Please. Please. Yeah.
My mic
Yeah. You
was,
are audible. Yeah. Yeah.
yeah. I'm working in ONGC, and because of oil and gas company, I understand the importance of energy transition. And I'm about to retire. I'll be 60 years in next coming April. So I want to
Oh,
contribute.
really?
I want to contribute in this area if given a chance. So I'm acquiring knowledge through this NPTEL also. I am doing some other course also on hydrogen correspondence. Because of job, it's very difficult to go for any class offline
Yeah.
course.
Yeah. Really. Yeah. Yeah. But
So
still, you are doing something for learn at this stage. Yeah. It's really. I appreciate it. Yeah.
yeah,
Thank you.
I want to do PhD also like you are doing, but maybe I'm not getting chance because of my posting here and there.
Yeah. Maybe after retirement you can do. Yeah. So there is
Uh,
no S bar for PhD, so you can still try.
so nice of you. Thank you.
Yeah.
Thank you.
Yeah.
Thank you.
Thank you. Good to meet you. Yeah. Thank you. Nitesh Shah.
Yeah, very good evening, sir. This is Nitesh, and as I am doing my master's in renewable energy and environment, but the hydrogen aspects are not much more cover in that area. But I just want to know, everywhere and like everyone is talking about the hydrogen, so it's very trending. And as this course is, like available by the one of the best faculty which is available in our country, so I just want to know what are the like even the negative aspect of this,
Nice.
like the futuristic things. That's all, and that's the
Yeah.
reason
Nice.
I'm here. And even
Thank
like
you.
how one yes, answer one more thing that like I just want to know that even how one individual can go ahead and start up all with these things if it's possible.
Yeah.
Thank you.
Nice. Thank you. Thank you. Priyanka Ambedkar.
Good evening, everyone. Myself, Priyank Ambadkar.
Priyanka. Sorry. Yeah.
Priyank Ambadkar. I am working with some thermal power industries, and my main motto is the green hydrogen, how it can be useful for the power sector. That is why I am as joined this course as a keen interest. Thank you.
Thank you. Priyanka S.
Hello everyone, I'm Priyanka Kujur and I'm working as a systems engineering product specialist in Cummins India Limited. I have around 12 years of experience, and the motivation for joining this course was to get an understanding on the energy transition that we are seeing from the conventional fuels like petroleum and diesel vehicles that we have. Specifically, since I'm from system engineering, this course will help me to really understand what would be the critical specifications or requirements that we need to understand for developing the exhaust gas processors or after treatment devices, so that we can further control the pollutants that might be emitted through the machines that use the hydrogen as a fuel.
Nice, thank you. Ramanathan.
Good evening, sir.
Yeah, good evening.
Good evening. My name is Ramanathan. I'm a chemical engineer. I'm working in a natural gas-based sponge iron production. Last 16 years I'm working. I believe the hydrogen is the future for the energy production. So for my improve my knowledge and curiosity, that's why I joined the course.
Oh, thank you. Ranjit.
Hi, this is Ranjit Kumar Prajapati. I am working in a renewable sector in last 10 years. So we are planning to execute the hydrogen plant, so that I am interested to join this course.
Nice, thank you. Ravi.
Hi, good evening all. My name is Ravi. I'm from India. Right now I am working in Jindal Shadid Iron and Steel Company. It is an MNC company. I'm working as an process engineer. I have a chemical engineer as the background, and I have total 18 years of experience in the iron and steel industry. The reason behind the hydrogen energy is that we are in transition from the natural gas to hydrogen, to use the hydrogen in our process and to drop the CO2 emission level. So there are a lot of process in that. So that is one of the reason. And I'm also open to all. So whatever the ideas or any discussion, I'm ready for
Yeah,
that.
sure.
Yeah. Thank you. Thank you.
Thank you. Thank you. Ravi Kumar.
Good evening.
Ritesh. Yeah, Ravi. Yeah, Ravi, please.
Yeah, I'm Ravi Kumar. I'm with my Indian Oil Corporation Limited. With the dual manager here. So I'd like to update my this thing on the hydrogen energy. So it's on my interest. I chose this program. I hope that will be helpful to me in my
Yeah, sure, sure.
career and syllabus.
Thank you. Ritesh.
Hello, sir. Myself,
Yes.
Ritesh Batare. Recently, I completed my chemical engineering from Mumbai University, and last year my project was green hydrogen. So I'm interested for this.
Okay, thank you. Rohit.
Hey, hi. I am Rohit, and I have been in renewable energy industry from last 12 years. Right now, I'm working with a company that is called MKS Atotech. There are many industries, but one of the core industries like chemical manufacturing for electroplating and coating processes, actually. The R&D center is in India, and we are already working on the coating part of like bipolar plates and catalytic coating over the electrodes and all. And the end plate. So my motive to join this course is to deep dive more into like technology part of the electrolyzers and the component and the BOP, basically balance of plant of the hydrogen generation system. Okay, so that I can know more about the material part and can think more about more and more about the surface finishing solutions for the industry. Yeah. Thank you.
Thank you. Thank you. Selva Kumar.
Good evening, Amit. Good evening, all.
Good evening.
Myself, Selva Kumar, process engineer. 17 years experience in technical service. Currently, I'm working with Jindal Shadid Iron and Steel, Oman. So, as you are aware, the iron and steel industry is slowly moving into hydrogen technology. There are a number of pilot scale ground level working is already in progress. So So I want to enrich myself in hydrogen, particularly in green hydrogen. So that is the motive why I'm here. Thank you. Thank you, everyone.
Thank you. Thank you. Shehbaz Khan. Okay. Veera Sakti R.
Good evening, sir.
Yeah, good evening.
Myself Veera Shakti. I'm currently pursuing chemical engineering at SSL College of Engineering. My senior recommend that hydrogen energy has better future scope, so that's why I choose this course.
Thank you. Shehbaz, are you there?
Hello, good evening, sir.
Yeah.
Am I audible now?
Yeah, you are audible. Now you are audible,
Yes, so
please.
myself Shehbaz Khan. Sir, I have done my BTech in petrochemicals, and thereafter that I have almost 3 years of experience in natural gas processing plant. So my motive is to enrich my knowledge regarding hydrogen energy, and I'm looking forward to working in this green renewable energy, green hydrogen project related activities. Thank you.
Okay, thank you. Vijay Kumar. Yeah, Vinay Kumar. Okay, Vinay Kumar. Okay.
Yeah, am I
Vijay
audible?
Kumar B. Yeah, now you are audible. Yeah, Vinay, please. Yeah. Yeah, Vinay, please continue. You are audible now. Okay, I think there is some issue with you, so we will come back to you later. Yaswant. Okay. So I think we have introduction of all participants. So it's good to know that we are having participation from both industry and academia. So I welcome you all again, and I request you please, like whenever we have any discussion, so those who are having relevant experience and industry experience, R&D experience, so please share your thoughts, because if the sessions are interactive, then it will be very good for both of us. So I will be also have some opportunity to learn from you, from your experience, and you will be able to learn from my experiences. So it will be from both sides. So whenever you have any query, so let's discuss.
Sure, that is a good idea. Sure.
Yeah. Thank you. Okay, so let's start with today's class. Just a minute. Okay, so my slides are visible, right?
Yes, yes.
Yes, yes.
Yeah. Okay. So those who joined late, so I'm again repeating. So the slides and this recording will be shared to you, and this meeting is being recorded. Okay, every Friday, 6 to 8 p.m. we will have this live session, and for any reason, if there is some changes, then uh, you will be informed from the NPTEL team about the new session timeline. Okay, so normally, but it will be on 6 to 8 p.m. So the course outline. So as you all know, this is a hydrogen energy course. So we will cover hydrogen production, hydrogen storage, hydrogen transportation, something about refueling stations, sensing and safety, global and Indian status. So these area will be covered in this course. In production part, production can be from fossil fuels and renewables. And storage part, the compressed storage, liquid state storage, solid state storage. So we will cover these aspects. Transportation, tube trailers, super vessels, and pipelines. So these are the area which will be covered in this course. So quickly, let's go through the week one summary. So if you have all gone through the videos, then maybe you are already aware of these things. So just quickly go through this, and after that we will solve some assignment question. So origin of the name hydrogen from hydro plus genes, meaning water and to produce. and it's most abundant element in the universe, like 75% of all matter in the universe. The energy LHV is 120 megajoule per kg, which is highest among all the elements. And hydrogen, when burnt in air, produce water. So it is considered as a clean fuel. So it's promote the use of diverse, domestic and sustainable energy resource. If we use hydrogen energy, so we can reduce import of fossil fuels and our dependence on them. Reduce GHG emissions from energy production and consumption. So as you all aware that every country all over the world, every country is moving towards green hydrogen because they have some targets for net zero emissions. So they have to fulfill by 2030. So the hydrogen is fuel that can that can help them to achieve the targets. So every industry, steel industry, oil industry, and like fertilizer industries, so they are main consumer of the hydrogen. So they are moving towards the green hydrogen part. So to reduce the GHG emissions, we need to focus on the green hydrogen. Increase the reliability and efficiency of the energy systems. H2 is widely used in existing chemical industry and refineries. Okay. Long-term large-scale storage which can be integrated with the renewables. Like basic properties. So mainly three isotopes are there: protium, deuterium, and tritium. And it's the lightest element and is 14 times lighter than air. And density of hydrogen is 0.08 kg per meter cube. So this is a important point, density. So density is very low as compared to other fuel. So that's why whenever we are talking about like hydrogen, then this is the major part, because if we are having a particular vessel, so that will have volume. So to have more hydrogen, we need to compress it to very high bar, like for 600 to 700 bar. So the pressure is a challenge. And whenever if you want to use the hydrogen in like for the vehicular application, then it's also have challenge. So the density is a major part. And it's colorless, odorless, tasteless, and flammable, non-corrosive, non-toxic. And these are the like triple point: temperature 13.8 Kelvin, pressure 7.2 kilopascal. So melting point 14 Kelvin atmospheric pressure, boiling point 20 Kelvin atmospheric pressure, and normal hydrogen is a mixture of ortho 75%, para is 25% only. So
Excuse
these are the
me.
properties. Yeah, sir.
Yeah, can you
Hello.
go to the previous slide?
Yes. Yeah.
In this during our session also, they have mentioned about ortho and para hydrogen. What is the difference between them? They have mentioned the atomic spin. It will be parallel and anti-parallel. So
Yeah.
what it means basically?
So difference actually I'm also not sure. So I have to look into this. So
Okay,
yeah,
no issue.
yeah.
That is
So
no
maybe
issue.
in the
And
next class, next
yeah,
class, yeah, we will discuss this in detail.
sure, sure. And the second thing is the critical point. So we are aware about the triple and the boiling points.
So like suppose if you want to store it, then up to this point, you can, by increasing the pressure, you can convert it into the liquid form. But after this, it will be not possible.
Okay.
Yeah.
So that is the maximum extent, right? That is the maximum
Yeah.
point. So that
Yeah,
it
maximum
is
point.
not
So
possible.
like it
Okay.
is in the gas form, so it is in the liquid. So if you increase the pressure, so it will go into liquid. Then there is a critical point. Yeah.
Okay, got it. Okay,
Yeah.
thank you.
So hydrogen is a powerful reducing agent. So it can react with like H2 plus copper oxide. So copper plus H2O, it can reduce. Reacts with oxides and chlorides. Reacts with salts like nitrates, and reacts with both metals and non-metals to form hydride. So this is also like it reacts with metal. So it can be used for storage also. And in the cleaning part, so you can see hydrogen reacting with sulfur and making H2S. So if your gas is having some elemental like some sulfur compound, so hydrogen is also used for the cleaning purpose also. It reacts violently with oxidizers. Diffusivity, it's very high. So in the air is for like 0.63 centimeter square per second. Methane is only 0.20 centimeter square per second, and gasoline is 0.08 only. So the molecule is very small than other gases, and it can diffuse through many metals considered airtight and or impermeable to other gases. This property makes hydrogen more difficult to contain than other gases. High buoyancy and diffusivity, so leaked hydrogen rise and become diluted very quickly. So it's a benefit, like it will dilute very quickly. Density, as we can like already discussed, 0.0899 kg per meter cube at NTP, and liquid hydrogen is 70.8 kg per meter cube, only 7% of that of water. Energy content, if you see the energy content, so compare the gasoline and hydrogen. So gasoline is 48.6 only, and hydrogen is HHV 141.8 and LHV 120 megajoule per kg. So if you consider the volume basis, so see the comparison. So the gasoline energy content is 31,000 megajoule per meter cube, and hydrogen is only 8,000 megajoule per meter cube. So see the difference. So that's why it's very like to have more energy. So it's a like a constraint in the hydrogen. So the volumetric energy is very less. If you see the mass based energy, it's very high, but volumetric energy, it is not that much. So like 690 bar, only 4500 megajoule per meter cube. So due to this, the storage is a issue for the hydrogen, because suppose if you want to store in a vessel, then the size of vessel will be very high, very large actually. So that's why there are different types of method for the storage. We will discuss in our future class what are the methods. But with this data, you can compare the challenge available with the hydrogen storage. Flammability range. So for the hydrogen, it is 4 to 75% concentration, gasoline 1 to 7.6, explosive range 15 to 59%. Auto ignition temperature is 585 degree for hydrogen, and gasoline to 40 to 460 degrees centigrade. So difficult to ignite hydrogen because air mixture on basis of heat alone without some additional ignition source, because due to this 585 degrees centigrade auto ignition temperature, so you need to have some additional source. Flame speed, so it's very high, 3.46 meter per second, and gasoline only 0.42 meter per second. So it's a benefit in the engines. So hydrogen engine can more closely approach the thermodynamic cycle. So these are all properties in a brief. So what are the use of hydrogen? So we can use in transportation, power, refineries, heating, space application, and industries. So mostly as of now, the major uses are industries and refineries. Some use it also in space application, but we are currently not so much using in the heating and transportation. It's started, but we are still exploring. And the power, so we are still exploring in the power. Some companies are working towards hydrogen engine, but I think it's still not fully available on commercial mass scale. So this is supply and demand. So the production, so you can see the 59% is coming from natural gas, 19% from coal, 0.7% from fossil fuel, 0.6% from oil, and 21% from H2 as a byproduct. So the major part is coming from natural gas, and it is coming from steam methane reforming process. So we will discuss that in further. So the currently 90 MT is global demands, and it is increasing very rapidly. The current utilization in refinery is 37.18 million ton, and industry 51 million ton, and other is 1.52 million ton. Industry in chemical and reduction of iron for steel making. So you can see the steel industries are also working towards green hydrogen, and I think in our class also, I think 2 or 3% from Jindal Steel. So maybe they are working towards green hydrogen for their steel making. For ammonia synthesis and methanol production, so 75% is for ammonia synthesis. So the ammonia is also used for hydrogen storage. Suppose if you have excess hydrogen, so you can store in that ammonia, and for later use, you can again produce hydrogen from the ammonia by ammonia cracking. So this is also used as a storage. We will discuss in our future class. Okay. So in India, we are having National Green Hydrogen Mission. So in that mission, we are having a target of 5 million metric ton of green hydrogen production by 2030. So that's why government of India is spending so much amount towards the green hydrogen. And recently, MNRE also floated some major projects like project call for green hydrogen, project on green hydrogen. So maybe many industries have submitted projects in that, and maybe in future we will see a good work in this sector. And in India, hydrogen valleys are also coming. So maybe in our next class or after that, I will discuss about some hydrogen valleys also. So there are various colors of hydrogen. Color coding of hydrogen is available. So you can say black, brown, blue, gray, turquoise, and like that. So it's coming from coal. So and more detail about the color coding we will discuss in future class. So basically it's coming from coal. So like the coding is dependent on the emission of carbon. How much carbon is there? So if there is more CO2 or more carbon, then it will be more like the black, and the green is totally from the renewable source, and there is no emission, no carbon emission, like from the electrolyzer if we are producing hydrogen from water or renewable energy, like that. So natural gas is gray hydrogen. So I think 1 kg of hydrogen from the steam methane reforming is producing around 9 to 10 kg of CO2. And coal is about, I think, 18 kg, 16 to 18 kg of CO2 per kg of hydrogen. So the color coding is based on what is the emission. So you can see the factor responsible for choice of the feedstock. So energy consumption, hydrogen yield, and emission. So these three factors are considered in the industries for the hydrogen production. So if you use natural gas, then the energy consumption is 42 kilojoule per mole, and hydrogen yield is 4 mole per mole of feed, and 10 tons of CO2 per ton of hydrogen. For the oil product, 50 kilojoule per mole and 2.7 mole hydrogen per mole feed, and 12 tons of CO2 per ton of H2. From the coal, so you can see it's 19 ton. That's why the color coding black is used for the coal. 19 ton CO2 per H2. And for water, so emission, there is no emission because if you are using water, so is only H2O, you are breaking it, hydrogen and oxygen will be there. And you are using, if you are using renewable energy, suppose if you are not using renewable energy, and the energy, the electricity that you are using in the electrolyzer, that is from your uh, thermal power plant, then that will not be considered as the green hydrogen. So it will be only considered green hydrogen when your all source of energy used in the production will be from a renewables only. Okay, so here you can see the natural gas is like the lowest energy consumption, highest hydrogen yield, and also the lowest emission in these compared feedstocks. So that's why it's very popular, and 59% of production is coming from natural gas only using steam methane reforming. So these are the ways like fossil fuels, so natural gas, oil, coal, renewables, biomass, and water. So natural gas and oil, we are using steam methane reforming, but still there are many other reformings are also possible, like partial oxidation, autothermal, combined reforming, dry reforming, plasma reforming, and steam iron process. We will look into these in our further classes. Like from coal and biomass, we can use gasification, pyrolysis, and combustion. So gasification will produce syngas. And biomass also biological method like fermentation, biophotolysis, metabolic process, and water photolysis, thermolysis, and electrolysis. So nowadays electrolysis is very popular. So currently I think global capacity for green hydrogen production from electrolyzers is around 4%. But it's increasing very rapidly. So this is the flow diagram of steam reforming plant. So you can see here, this is the input, natural gas. Then we are having a cleaning unit. So because natural gas may have some impurities, sulfur. So we need to remove the impurities because the impurities can deactivate the catalyst that will be used in the reformer. So if your catalyst is being deactivated by the impurities, then you will not get the yield as expected. So first clean it, then the compressor. So it's compressing it to 16 bar because the PSA works at high pressure for the hydrogen separation, and also in the industries you require the hydrogen at a very high pressure, so that's why you are compressing it. And then heater to preheat the gas because the reformer is operating at 850 to 950 degrees centigrade. You require high heat. So for the steam reforming, the energy requirement is 206 kilojoule per mole. So you can see in these tubes there is catalyst and also there are burners. So you are burning some fuel to maintain the temperature, and in this tube you are adding the natural gas, and you are having a steam generator, so you are adding the steam. So you are maintaining the ratio also because you have to maintain the ratio, steam to methane, steam to carbon ratio. Okay, otherwise there will be some carbon deposition. So for the steam methane reforming, it is from 2.5 to 3 normally we use, but the higher is the better. So then you can see there is a heat exchanger. So you are using the exhaust gas from the reformer heat to preheat the natural gas and also to generate steam. Then there is a water gas shift reactor because there will be CO also. You can see 8.5% is CO. So you need to convert this CO into hydrogen and CO2. So you will use a water gas shift reactor. So it is operating at 350 degrees centigrade and is further converting the CO into hydrogen using this reaction. And then it is going to the PSA. So PSA will separate out the pure hydrogen, and the remaining PSA off gas, or you can say tail gas, will again go to the combustor, and that will be burned in the combustor, and the heat will be used for the steam reforming. So this is a flow diagram. So the major part is the cleaning unit, compressor, preheater, reformer, water gas shift reactor. Here we are using PSA. So we are only having a high temperature water gas shift reactor. If you are having a different method for the hydrogen separation, so maybe you will need another water gas shift reactor, low temperature water gas shift reactor. So it depends on your hydrogen cleaning process. Okay, so this is a very brief about our previous week. So now let's start with the questions. So I advise you to, whenever you come to the live session, so please go through the previous week classes so that it will be easy to understand these questions, and you will also participate in the discussion. The question number 1 is, based on the quenching distance of hydrogen, the possibility is that it has a no tendency to backfire, flame that travel far away from cylinder, and hydrogen flames are difficult to extinguish. Hydrogen will lead to embrittlement. So take 1 to 2 minutes, think about it and let me know the answer.
Hydrogen will lead to embrittlement because hydrogen very reactive to metal.
Okay.
And size is very small. It is also reason for embrittlement.
Hydrogen flames are difficult to extinguish.
So we have one answer D.
Option number 3.
So we have, I think, more students are towards option number 3. So what is this quenching distance is representing? Anybody?
Sir, what does quenching distance mean?
Yeah, I am asking the same. So what is this representing, quenching distance?
So basically, I'm right or wrong, I don't know. The distance between the extinguisher and the flame. So for hydrogen, it is very narrow to extinguish.
Okay, so I think we have already covered this in our class. So yeah, so this is the quenching distance. So the quenching distance describes the flame extinguishing properties of a fuel, relates to the distance from the cylinder wall that the flame extinguishes due to heat losses. So the distance for the hydrogen is 0.4 mm and for the gasoline it is 2 mm. So hydrogen flames are difficult to extinguish due to very narrow distance and tendency to backfire. So the quenching distance, so here you can see the methane is at this range for propane and gasoline. So it is 0.644 of hydrogen. So it describes the flame extinguishing property of a fuel relates to the distance from the cylinder wall that the flame extinguishes due to heat losses. So now see the options. So the first is no tendency to backfire. So there is tendency to backfire because distance is very narrow. So it's only 0.64 mm. So it can backfire. So option 1 is wrong. Then second, flame that travel far away from cylinder. So as per distance, is it far away from cylinder or not? Like this is your cylinder. It's containing the hydrogen, and if you are giving a spark here, so the distance between the flame and the cylinder, it is very narrow. So it's only 0.6, so it will backfire. Okay, and it's also difficult to extinguish. Hydrogen will lead to embrittlement? No, because it will a different aspect. The correct option will be flames are difficult to extinguish. Okay, because its tendency to backfire. So it's near to cylinder. So option A is wrong, B is wrong, D is wrong. So C is correct.
Hello.
Yeah.
So I have a doubt.
Yeah.
Sir, hydrogen, I mean, the bond distance and bond angle would have any impact on the extinguishability in hydrogen?
Hydrogen?
Like to extinguish, will the bond angle and bond length, does it have any influence over it?
I think that is very on like the bond angle and those things are on atomic level. So I don't think so. Whenever you are having like a fire situation, so that will any effect on the extinguishing property.
Sure.
But maybe you can look it about more. So in my opinion, I think that will don't have any impact on this. Okay, let's move to the next question. So what is the lower flammability limit of hydrogen in the air under NTP conditions? Lower flammability limit. So we have studied lower and higher limit. So what is the lower limit? 10%, 12%, 4%, 8% by volume, 20% by volume, 25% by volume.
4%.
Okay, so what is the meaning of this flammability limit?
Out of the total volume, if 4% or more of hydrogen is present, it can be.
I think your voice was not clear at the end. Please repeat.
Yeah, out of the total volume of air, if the percentage of hydrogen is 4% or more, it can catch fire.
Okay.
Yeah.
So suppose if it is 3%, then what will happen?
It is not sufficient for the catching the flame.
And do you need a ignition source or not? If suppose there is 5% of hydrogen in a particular environment, so by volume it is 5% in the air. So do you think do we need an ignition source like a spark, or it will be self ignite?
No, we need a spark to ignite the flame.
Yeah. Okay. And what is the higher flammability limit? What is so we have one option, 4% is the lower limit, and what is the higher limit?
75%.
75%.
Okay.
70%.
75.
Okay. So what is the meaning of the 75%?
70% of the volume, if hydrogen is there, then along with the air, there is possibility of fire.
Okay. And suppose if it is 80%, then what will happen?
The fuel is highly enriched, so
Yeah.
the possibility is very low for fire.
Yeah. So there will be very rich fuel mixture. So the possibility will be very low. So the lower limit is 4%, and it is between 4 to 75%. Higher limit is 75%. So below 4, it is very lean mixture. Above 75, very rich mixture. In between, it is possible for the any ignition or like any chance of fire. So the correct answer is 4% by volume. In the color coded assigned to hydrogen based on source used for hydrogen production, which color represents the hydrogen production from renewables?
Green.
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 Okay.
Green.
So
Yeah,
we
green.
all know green is representing the renewable. So what is the meaning of black?
High
Black
percentage
from
of
coal.
Black
coal.
represent from coal.
Coal.
Non-renewable, some coal.
So black
Percentage
represent coal.
high generation of CO2.
Yeah, high generation of CO2. And what is the brown?
From lignite.
Brown is from
Lignite.
Generated
lignite.
from fossil fuel.
And what is the blue?
Blue is from fossil fuel along with CCU, carbon capture unit.
Yeah, it's very important. So you are still generating from the fossil fuel, but you are capturing the carbon. So you are having a separate unit, carbon capture in CCUS unit. So that unit is capturing the carbon and ensuring the utilization of this. So that's why it is blue. So the cost of blue hydrogen is little bit higher than other mode of hydrogen. So before green hydrogen, this blue hydrogen was very popular, but due to the cost, it was not used widely. And green, we know from the renewables. Okay. So I think many of you are from industry. So what is the exact definition of green hydrogen per National Green Hydrogen Mission of India?
It is 2 kg CO2 production per kg of hydrogen.
Yeah, nice. Thank you. So if you are having like in complete process, if you are having 2 kg of CO2 there, still it will be considered as green hydrogen. Okay, in the complete process, am I right?
Yes, yes.
Yeah. So suppose if you are like, because whenever you are producing hydrogen, so there will be different processes. Okay, so you need to first produce, maybe you need to also pre-treat the feedstock. You are having some other units, you are using some kind of like extra electricity for some pumps or like there, so you are not using renewable electricity there. So all the process that are involved in the production, so you need to calculate the carbon emission related to per kg of hydrogen, and you need to find the value. If your value is less than 2 kg CO2 per kg of hydrogen, then only it can be considered green hydrogen. Okay, suppose if you are having only electrolyzer and you are using the renewable electricity, okay, it's fine. But for compressing, okay, you need a multi-stage compression, high bar compression, like to compress hydrogen to 700 bar, and you are using the electricity from power plant, then you need, actually you are using, you are not using renewable electricity. So then you need to consider, okay, you are in the compression, you are using, because you are not emitting the CO2 at your location, but somewhere CO2 has already emitted. Okay, so you need to consider that. So in the whole process, 2 kg of CO2 per kg of hydrogen is allowed. Beyond that, it will not consider as green hydrogen. So whenever and for more detail, refer to the government policy document. So what is the exact definition of green hydrogen? That's very important. For the blue, you need to install a carbon capture unit. For the brown, and black is from the coal, and brown is like little bit pure coal, or like the process is not that much prone to the carbon emission. So the answer is green hydrogen. Okay, from the renewables. Hydrogen production from which of the following feedstock result in maximum CO2 emissions? Natural gas, water, oil products, coal.
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 Okay.
Coal.
So okay, so the coal is ranking is 1. Second rank will be
Oil.
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 Oil products. Natural gas.
Oil
Water.
products.
Natural gas and water.
yeah. So water, if you are using water, then theoretically we are only breaking the bond H2O. So H2 will be separate and oxygen will be separated. Okay. And natural gas, we know using steam methane reforming, widely used method. So 1 kg of hydrogen emits around 10 kg of CO2. SMR stands for
Steam methane reforming.
Steam methane reforming.
yeah.
Steam
So
methane reforming.
it's very clear. It's steam methane reforming. If carbon dioxide is used as oxidant, then the reforming process is known as SMR, partial oxidation, dry reforming.
Dry reforming.
Dry reforming.
Okay. Okay. Is it called dry reforming? Anybody, can you tell me the reaction of the dry reforming?
CO2 plus CH4 gives CO and hydrogen.
Yeah, then
CO
I
and
think
hydrogen.
methane reacts with CO2 that gives CO and H2.
is it correct?
You have to balance.
Yeah, we have to balance.
2
Yeah.
CO plus 3 H2. 2 CO plus 3 H2.
No, 3H2 is in the steam methane reforming. Here you can see is only CH4.
Yeah.
So it's 2H2. Okay, so this is the difference. So if you compare, so sorry for my writing, actually I'm using mouse, so maybe from the next class I will using a pen. So H2O, so okay, so you see here the CO and H2 an equal proportion, and here the hydrogen is more. So these reforming techniques, so you can see the combination. So in industries, suppose if you want to have the ratio of hydrogen to CO like 1, then they prefer to have dry reforming. So it's also an important factor to consider the reaction. And if you want to more hydrogen as compared to CO, then you will go for the steam reforming.
So the first reaction is also the production of syngas reaction. Is that right?
So the syngas is the combination of hydrogen and carbon monoxide. So it's only the ratio. So in both cases, you can say it's syngas. Only the thing is the ratio is varying hydrogen to CO. So in this steam reforming, if you compare the ratio of H2 to CO is 3. And in the dry reforming, it's 1.
Okay.
Yeah. So steam reforming covered dry. So what is the energy requirement for steam reforming and dry reforming? For steam reforming, what is the energy requirement? So because you can see we have to break the bond, new bonds will be formed. So if you have seen the tutorial lecture or also the notes, so what is the enthalpy of formation required?
Steam reforming 192 kilojoule per mole required.
For the steam reforming, it is 206 kilojoule per mole. And for the dry reforming,
Dry reforming 236 kilojoule per mole.
yeah, it's 236, yeah, or 247. Please just confirm.
Okay.
So it's around 236 or 247. Yeah, please check it. Okay. So you can see, so which reaction will be more preferable?
Steam methane.
Yeah, so for the steam methane reforming, the energy requirement is less as compared to dry reforming. So the steam reforming will be preferred. Okay. And also the side reaction. So maybe in one class we can discuss about side reactions also, because whenever we are having a reforming unit, okay, and we are having, like, suppose if you are using a mixture of these, you are having CH4, CO2 and also H2O. Suppose if you are only using CH4, H2O, then okay, you know, this will be the prevailing reaction and there will be some side reaction. But if I'm also using, suppose I'm using a biogas, then there will be CH4 and CO2 and they will not be in equal proportion, and I'm also adding H2O there. Okay, so basically I'm having bi-reforming. Then we have to do the calculation. So which reaction will be preferred and what about the side reaction? Okay, so we will look into, I think in a class I can discuss about those things in detail. So for now, dry reforming requires more energy as compared to steam reforming, and the ratio of H2 to CO in dry reforming is 1 and in the steam reforming is 3. And what about the this partial oxidation? Anybody? So basically in partial oxidation, we will use a stream of O2, oxygen. Okay, so there will be some partial oxidation and that will provide the heat for reforming. Okay, so your net heat requirement will be lowered. And similarly in autothermal reforming, it is a combination of steam and partial oxidation. So the answer for this question is dry reforming. What is the main reason for deactivation of catalyst in the steam reforming? So, you know, in steam reforming, the deactivation of catalyst is there. So we have 4 options: high temperature, coke deposition, high pressure region, and presence of steam.
Coke deposition.
Coke deposition.
Coke deposition.
Okay, so everybody is saying that the correct answer is B. Okay. Now let me know why answer A is wrong.
Because at high temperature, that is the basic requirement for not allowing coke to deposit on the catalyst. That is why we keep around 900 or something.
Yeah, nice.
But
So
temperature
basic,
will be more.
yeah. So there are the reactions that are responsible for carbon deposition is the methane cracking, okay, Bordeaux reaction, and so these reactions are, and also the reverse water gas shift reaction is there. and also the cracking of CO, I think, yeah. So these reactions are more favorable at lower temperature. If you are having high temperature, then if you compare the Gibbs free energy of these reactions, so these reactions will become less favorable. Okay, that's why we operate at high temperature, so that only the reforming reaction like steam reforming, dry reforming, only those reactions will happen. So the high temperature is not a reason for the deactivation, it is the favorable condition to avoid the deactivation. Then the high pressure region, why this option is wrong?
Erosion.
Erosion, how?
Uh, because of when we'll increase the pressure, the velocities will also increase, and due to high velocity, erosion will happen.
Okay. Okay, so how are you connecting the erosion to the deactivation of catalysts?
Deactivation of catalyst. Deactivation, high pressure.
Okay, so if you are having like high pressure regions, so the pressure is not a limiting factor or driving factor for the coke deposition in these, like in the steam reforming mostly. Okay, because steam reforming is more favorable at lower pressures.
Right.
Okay, but still you are having high pressure, then it's okay, but it is not a reason for the deactivation. The erosion, I don't think so it will happen, but okay, you can look more deeper about this.
But metallurgy we need to.
Yeah, Selva
But
Kumar, yeah.
metallurgy we need to see in this condition of what will be the thickness of the tubes and the MOC of the tubes.
Yeah, there are, yeah, maybe there are more options because I'm not from the material background and I don't know much detail about it. So you can look more deeper. And the next is the presence of steam. So if we are having like more steam, then automatically there will be very less chance of side reactions. And also the carbon gasification will be also there with presence of steam. So the correct answer is coke deposition. The main reason of deactivation of catalyst in the steam reforming is coke deposition. And why this will happen?
I have one query in this regard.
Yeah.
Presence of steam actually in if you see the this steam reforming this flow diagram in slide there the thickness actually in length of the tubes and the thickness both were mentioned like 7.5 to 12 meter length and the thickness of 1 to 2 centimeter.
Okay.
So is it in this case when the the carbon deposition is possible, is it possible to maintain this thickness? Because in that
No, I
condition the
think
velocity will increase and the reaction will not happen
so.
as per requirement.
Thickness and I think thickness and those detail will be as per your flow conditions also. The length and all
Right.
these requirement, the design constraint based on the flow.
Right.
So in this slide, I cannot see they have mentioned the thickness or these things. Maybe you have seen some other slide. Maybe it have mentioned so, but that only for a reference case to show you. details. That is not a standard one, but the design will be only decided because the velocity, the retention time, it's a very, these parameters are very important for the reactions to complete. Okay.
Right.
Yeah.
Right.
So the geometry of the tubes will be only decided as per the flow condition, steam to
Right.
carbon ratio. So these are the condition. So based on that only the design will be decided. And I think normally whenever you want to install a plant, then first you will model it. Yeah, so maybe that particular the geometry you are talking about, maybe that is only for reference case. They have just mentioned it for a reference, not for the particular thing.
Okay. Okay.
Yeah. So here you can see. So what was the question? So question was about.
In case
The
deposition will happen, then what should we have to do in that case?
So the deposition is, if deposition happens, then if it is not of much scale, then normally if you supply some more amount of steam, then that carbon will react with the steam and like the gasification reaction will be there. Okay, but if the coke deposition is in a much extent, then your catalyst will be deactivated. So that's why I always have some extra amount of steam. So generally we use uh, 3:1 steam to carbon is 3. Steam to carbon is ratio is 3. Yeah, in steam reforming. Yeah, so we should have extra steam to avoid the coke deposition.
Okay.
Yeah,
And
because
the second,
you know the
please,
catalyst.
please.
Yeah, so because if suppose these are the catalyst, okay, so when the carbon will deposit, so it will cover the surface, the active surface, and it will
Right.
start grow. It will start growing actually. So it will cover the whole area. Okay, so it will totally deactivate the catalyst.
Right.
Yeah.
What kind of catalyst we use?
So generally there are different types of catalyst available in the market, but widely used catalyst is nickel.
Nickel.
So due to
And the
its
shape?
cost, easy availability, shape you can decide. So there are different kind of shapes available. So it's per the condition. Just so as the thing is that the surface area. So you should have as much as surface area. So the shape, there are multiple options available. So in the lectures also, ma'am have discussed this. So you can refer to the lectures.
Okay. Thank you.
Sir,
Thank
I
you.
have one question.
Yeah.
Now the catalyst is playing a major role in the reforming process. Okay, when the
Right.
coke deposition happens, then it will disturb the whole process of H2 production. Is it right?
Yeah, right. Yeah,
Okay.
right.
So is there any online cleaning or online removal technology or any device during the process so that we can remove the coke deposition on the catalyst so that we will not shut down the whole process and the generation of the H2 will be continued?
Yeah, there are some like other reforming methods are also there. So in those reforming methods, we will discuss in further class. For like for steam reforming, you can the only thing that you can do is supply some extra amount of steam. So that can you will have chance to remove the carbon. Okay, but up to a certain extent.
Yes, sir. We can put an extra regenerator for the catalyst, like FCC, fluid catalytic cracking unit. They use a regenerator for catalyst regeneration.
Yeah, so you like this, maybe some technology are there, but like but there are different reforming methods are also there. In those methods there are these like regional step is also involved. So if there is this kind of thing happens, then there is a like two reactors, so they can regenerate it, and there's a very less chance of carbon deposition and deactivation of catalyst.
Okay.
So Amit, here one question. So
Yeah.
in SMR process, so we are operating high temperature. So what is the consequence if we maintaining high pressure?
So the reactions are favorable at lower pressure, but the consequence is I think normally industry people are operating at higher pressure only. But maybe if the pressure is higher, so the reaction kinetics will affect. So because there are many side reactions are also there, so maybe those are affected by the pressure. So basically, if you are operating at higher pressure, then the velocity will also change, the gas velocity, and all things will be different. So I'm not know in the detail about what will be the direct consequence in the on the reaction, but the reaction kinetics will be disturbed at higher pressure.
Okay.
Yeah.
Okay, thank you.
Thank you.
What is the suitable
What-
temperature and pressure required for reaction?
So the reaction, the temperature is around more than 850 degree. That is the best temperature, 850 to 950. But still you can operate around 800 with extra amount of steam, and there will be some, maybe some side reaction will be there, but 850 is good. And the pressure normally, like in industry, I think it is operated around 1.5 to 2.5 megapascal. But generally, like if you theoretically 2-3 bar is fine also.
Is there any restriction for velocity?
So as I already told you, because these things are, you have to look in the kinetic model, because the reaction kinetics is very complex. You having a particular catalyst, because the reaction kinetics will change as per the catalyst. So whenever you want to have a steam reforming reactor, then you need to know the catalyst. Okay, what will be the your required feed velocity, feedstock availability, like these things are very important. The temperature, the pressure. So these things will uh, affect the reaction kinetics. So for each different type of catalyst, it can be different. So the best thing is to model the thing, model the reactor. So there are already
Excuse me.
some, yeah.
So in future class, whether you're going to teach about the kinetics, the reaction
So
kinetics.
reaction kinetics, I think reaction kinetics is not covered in this course. So in this course, we have covered the hydrogen production, storage, transportation, and these things. So this reaction kinetics is separate chemical course. So you can find some course on NPTEL also. So because reaction kinetics is very complex. So I am not an expert of reaction kinetics, but I know something about these reaction kinetics. So uh, it's really good to learn this. So you can find a suitable course on the NPTEL website. Yeah. So maybe
Okay,
it will
dear
be
Master.
from,
Okay.
yeah, it will be from chemical engineering background.
Just a thought, as it was discussed, when the velocity is very high, I assume there's going to be erosion also. Just a thought.
Okay. Yeah. So yeah, maybe I'm not sure about this. So maybe, yeah. So you mean to say the erosion of the catalyst?
No, not the catalyst.
What
The
is the
erosion of the vessel, I mean.
okay, erosion of the vessels? Okay, okay.
Actually, we are using here methane reformer here in our DRI plant, direct reduced ion plant. As
Okay.
you said, the operating pressure is between 1 to 1.8 or 2 bar.
No. 1.5 in industries they are using around 1.5 to 2.5 megapascal. Yeah, like 20 bar, 15 20 bar. Yeah.
Yeah.
But
But
you
in
can,
our process, it is 1.5 to 2 bar.
yeah.
Because the
Actually,
process is slightly
it's
different.
suitable at, yeah, it's
Yeah.
suitable at lower pressure. Yeah. If you're
Yes,
operating
yes.
at 2-3 bar, it's good.
Yeah, and there are also the same DRI plants with steam reforming, where they operate like 3 to 4 or 5 bar. So the process slightly differs depending upon the conditions.
Yeah. So it depends on the conditions. Yeah.
Yeah, and the higher the hydrogen percentage in the composition, higher the pressure you have to give inside the reactor or the furnace.
Yeah, right, right. Because for the hydrogen separation, if you are using the PSA, then for 99.99% purity, you need to go for higher pressure, 20 to 30 bar. After that pressure only, you will have more purity.
Okay.
Okay, so let's move further. So the typical steam to carbon ratio for the SMR process. So we have already covered it. So 2.5 to 3. The most widely used shape of catalyst in a steam reforming process. So we can use multiple shapes. I think one of you have already asked this question. So rings, gear wheel, solid pellets, and multi-channel catalyst with holes. So these are the available shapes. So different shapes are available, but most widely used one.
That is multi-channel catalyst with holes.
Yeah, correct. So this one is the most widely used. The ignition energy for hydrogen is
0.04.
anybody?
0.02.
Yes. So the correct answer is 0.02. And what is the hydrogen flame speed at stoichiometric ratio? So these are direct
3.46.
question actual database. So we cannot discuss this question. So the direct answer is 3.46 meter per second. The lowest energy consumption in hydrogen production.
Water. Oh, sorry. The other way. It
Natural
should be the
gas.
other way.
Yeah,
Natural gas.
natural
Natural
gas.
gas.
Yeah. And so this is the first and second.
Oil.
Oil.
Oil will be second, the coal will be third, and the water will be fourth.
Water is the last.
So any of you like, do you know how much of electricity, like in kilowatt hour, we need to supply for the electrolysis?
53 kilowatt hour per kg of hydrogen.
45, roughly 50. 50.
Roughly, yeah,
50 to
53. I think
55.
53 is the nearest answer. Yeah, 53 unit of electricity required for the electrolysis. Okay, to produce 1 kg of hydrogen. Pre-reforming is used when feedstock is
Higher hydrocarbons.
Higher carbon.
Higher hydrocarbons.
yeah.
Option B.
And what is the meaning of pre-reforming?
Converting the higher hydrocarbon into lower hydrocarbons.
Yeah, right. And why we are doing this? Suppose we are having a reactor and we can do all the reaction in one reactor only. Then what will be the issue if we are using like higher hydrocarbon directly in a steam methane reforming reactor?
Maybe
high
more
energy.
carbon soak deposition will be higher.
Carbon deposition in the
Yes.
catalyst.
Carbon deposition will be higher. And also because maybe in your the catalyst, so if deposition is there, then that will be deactivated. And if you are using if you are already having a pre-reforming reactor, so you can use some like cheap catalyst there for pre-reforming. If suppose there is some deposition, you can replace them with lower cost as compared to your main reactor. So that is also a point. And also you can convert into lower hydrocarbons and easily maintain the steam to carbon ratio. Otherwise, if you are using in the same, then you need to maintain a very high steam to carbon ratio. So your requirement of steam will increase. And so basically your requirement for maintaining the temperature will increase, like 850 degrees centigrade. So there are multiple reasons for this. So for high hydrocarbons, we use pre-reforming and then main reforming.
Yes, Amitji.
Yeah, please.
By installing the pre-reforming in a reformer, then how much life we can increase the catalyst, how much life of reformer catalyst will be increased?
So I don't have exact number like how much, but yeah, it is a good idea to have a pre-reformer. Otherwise, you will have a severe carbon deposition.
Okay, in terms of life, can we say that it's about 50%, 70% life
Maybe so I cannot comment on this, but maybe there are some studies, so you can find on some literatures. Maybe somebody have already done a study in terms of life comparison. So you can
Actually,
search it.
yeah, sorry to interrupt. In our industry, we are using a nickel-based catalyst for the reforming. Generally, the vendor says like 5 to 6 years as the life year for the catalyst, but it purely depends upon the gas quality and the temperature at which we are operating. So a lot of factors are there. But
Yeah.
the vendor says it is 5 to 6 years. The life is there, and
For
we have
the
like
reforming or
9
for the
to
pre-reforming? So you are having a reforming reactor
reforming.
or a pre-reforming reactor?
Reforming. Yeah, we don't have pre-reforming, but we have natural gas pre-treatment plant to settle down the higher hydrocarbons.
Okay.
Yeah, so the life is like 5 to 6 years.
Okay. For the reforming reactor of nickel catalyst.
Yes, 9 to 12% of nickel is there, and
Okay.
rest is like aluminum oxide, Al2O3 is there.
Yeah, as a support. Yeah. Okay.
Yes. Okay.
Okay. Okay. So the syngas consists of
CO and H2.
yeah.
CO and H2.
So syngas is CO and H2.
H2.
So only thing is that if we are using a different reforming technique, then basically we are changing the ratio of COH2 or H2CO. Okay, but still they are syngas. Why high steam to carbon ratio is required during SMR?
To avoid coke deposition.
To avoid coke deposition.
Yeah. So we all know that steam to carbon ratio do not promote the coke deposition, so it is wrong. To reduce amount of waste gas, no. So waste gas is not depend on the steam to, so it actually depend. So if you are having more steam to carbon ratio, so what will be the waste gas will be high or low? The amount will be higher or lower?
Higher.
Or lower.
Okay, why
It should
lower?
be lower.
Because we get more of hydrogen after there is a shift reaction and hydrogen is in production of hydrogen increases.
No, suppose no, the mass balance na, if you okay, the hydrogen will be there, so in the molar fraction that will change, but if we are comparing the mass value, then if you are using steam to more steam, then basically you are increasing the flow rate, na, total flow rate.
Yeah,
So the
right.
amount of waste gas will increase. So it will not reduce the amount. Yeah, it will increase. So basically you are adding, suppose if you are having 1 kg of methane, then maybe you are having 3 kg of steam, and if you are making it 4 kg, so total mass, if you compare it, is become 5 kg. So there will be some hydrogen will be there, but the net, if you compare the mass balance, so it will be higher. So the balance will be, the waste gas will become higher. To reduce the hydrogen yield, no, because if you are having proper steam to carbon ratio, then only the reaction will be completed as we require. Otherwise, some side reaction will be there, and the coke deposition will be there. The catalyst will be deactivated, and the hydrogen yield will reduce. So higher steam to carbon ratio ensure higher hydrogen yield. So to avoid the coke deposition, this one is only correct. Okay, so answer is D. So just 1 point. So in NPTEL exam, so my advice is to go through all the option like we are doing here. So don't think only one answer will be correct. Sometimes multiple answer are also correct. So try to go into detail of each option. Okay, so that you know, okay, this option is wrong and this option is correct. Because sometimes maybe C or D both correct, and they will not mention that more than one options are correct, like that. So it's better to go through all options and try to find the correct answer with proper reasoning.
And Amit, in this regard, whether it is always multiple choice exam or it's a subjective also?
No, it will be not subjective. It will be multiple choice, or maybe some fill in the blanks can be also there, where you have to enter the value. Like suppose if you are having a numerical, then maybe sometimes they don't give you the options. You need to type the answer,
Yeah.
the
Okay.
numerical value.
Thank you.
So what is the reaction enthalpy for the decomposition of methane as per the following reaction? CH4 carbon plus 2 H2. Okay, so try to remember this. So the answer is 74.6 kilojoule per mole. So this reaction require this much of energy. Water gas shift reaction is an endothermic, exothermic, thermoneutral, or
Exothermic.
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 and what is the
Exothermic.
amount of the energy released in the water gas shift reaction?
It's a minimal.
No, I'm asking the number. What is the amount in number?
Around 40 kilojoule, I think.
Yeah, it's 41 kilojoule per mole of energy will be released in water gas shift reaction. And what is the reaction?
Exothermic.
CO plus H2 gives CO2 plus H2.
CO react with the steam,
Yes.
produce CO2 plus
Hydrogen.
H2. Okay. So this is the water gas shift reaction. And what about the reverse water gas shift reaction? So in reverse water gas shift reaction, your CO2 will react with H2 and convert CO and H2O. Okay, so sometime suppose you are having a steam reforming reactor and you are producing H2, and also there will be suppose CO2 will be there. So if your operating parameters are not favorable in the only steam reforming reaction, and like there your temperature is promoting the reverse water gas shift reaction, then what will happen? The H2 which was generated from the steam methane reforming reaction will react with the CO2 and again produce CO and H2. Okay, so basically your outlet gas from the reforming reactor will be higher in steam and CO. So hydrogen yield will decrease. So your aim will be to eliminate the possibility of reverse water gas shift reaction. So water gas shift reaction is good. It is favorable to you, but you want to avoid the reverse water gas shift reaction. So at higher temperature, around 819 below this and more than I think 700, there is chances of reverse water gas shift reaction. Okay, so you need to look into the exact temperature range at which temperature range it is favorable. So you need to avoid that. Okay, otherwise your H2 concentration in the outlet gas will decrease and the amount of steam will increase and CO will increase. So the answer is exothermic. So in PSA process, adsorption step is carried out at and regeneration is carried out at, respectively?
High pressure, low temperature.
Yeah, high pressure, low temperature.
I think temperature is not mentioned in the option.
High pressure and low pressure.
Yeah.
Yes, high pressure, low pressure.
High pressure and lower pressure. Okay. So the PSA process adsorption step is carried out at higher pressure and regeneration is carried out at lower. So what is the meaning of the adsorption step? Anybody from the industry? Are you having any PSA there? If you want to share the working of PSA, it will be good for us.
In our industry, it is not there.
Okay.
But I have came across the PSC operation.
Okay.
So basically, it requires higher pressure for absorption of the particular component. And
Okay.
the regeneration is the recovery unit, where the pressure is not required that much. So the molecular sieve or the material can regenerate and it will come back to its original form.
Yeah, right.
So again, it can be used.
Yeah. So suppose in the adsorption step, we put higher pressure and the like material molecular sieve, and like suppose if you are using biogas upgradation, then they use geolite. So different kinds of methods are there, and as per the purity, okay, you can change the number of towers and also the pressure. So nowadays the VPSA are also there. Okay, so PSA, VPSA. So as per the gas component, as per the purity, different systems are there. For the hydrogen, we use high pressure due to the hydrogen molecule. You know, it's very small, lighter. Okay, and so in the first step, we use high pressure. So at that pressure, only hydrogen element will pass through the tower, and all the other gases will be adsorbed on the molecular sieve or the element that you are using in the inside the PSA. So the hydrogen will pass and leave from the top, and in the regeneration you will release the pressure. So when you release the pressure, so the molecule that was adsorbed on particular molecular sieve, that will be released to the tail gas. Okay, or like it will go towards the again the next tower. So it depends on the configuration which we are using. So these are the steps involved. So the higher pressure and lower pressure is the correct answer. What is the main issue of using nickel as catalyst? Prone to deactivation and sintering, stops reaction, cost effective, unstable operation.
It is like A and C. C
No,
is the cost
main issue. Main issue, I think the cost
C is
effective.
the
Nickel is a
prone
cost
to
effective.
deactivation. A is
Yeah.
the answer.
So as we all know that nickel is very prone to deactivation with due to the carbon deposition. So that's why the answer is A. Stops reaction, no. Cost effective, it is widely available. Unstable operation, no. It gives a stable operation. The correct answer is A. Prone to deactivation and sintering. And what is the temperature condition for pre-reforming of higher hydrocarbons?
Option B, 400 to 550 degrees centigrade.
Yeah, so option B is the answer. So what is this range? Range of A is for the reforming reactor.
Reforming.
And what about this range D?
It is low temperature water gas shift reaction.
Yeah, it's low temperature water gas shift reactor. Okay. And suppose if I am using this this temperature range in a pre-reforming reactor, then what will happen?
The reaction will not take place.
Okay.
Irreversible reaction.
There will be some reactions, but the extent of reaction will be not full, and the side reactions that we have discussed, you need to see the temperature profile for those reactions. So maybe those can happen and deposit the carbon. And this range 600 to 700.
High temperature water gas shift reaction.
Yeah. So no, it's not for high temperature water gas shift reaction. That is less than 400 degree.
Yeah, it is
400,
near to 300 to
300 to
400.
400. Yeah, yeah.
Yeah.
So you can use this for also the pre-reforming, but there is, because for reforming, if you are using this temperature, then what is the meaning to use this for the pre-reforming? So basically in the pre-reforming reactor itself, your most of the gas will be reformed. Suppose you're pre-reforming, if you are using this temperature range, then maybe the 50% of your reforming is happening, or maybe the 40% reforming is happening. But if you are using this range, then maybe the 70% reforming is already there, and there will be severe side reaction because this temperature is very prone to severe side reactions, the bordered reaction, and also the 700 degree. No, it cannot. For the methane cracking, that will be more than 700, I think. Yeah. So, but it's still not advisable. So this one is the medium temperature 4 to 550 is for pre-reforming, and then you can use the reforming temperature.
I have a doubt here
Yeah.
regarding this temperature. So whether the reaction is going to complete within this temperature range, or some composition of reactant will be there in the product.
So suppose a reaction, like suppose a reaction require a particular energy. Okay.
Okay.
So like 1 mole of reaction required 206 kilojoule per mole. You know that energy, like for the steam methane reforming. And maybe if you are having this temperature, like lower temperature, so the some part of, like, some molecules will be able to have that energy, not all the molecules, na.
Yes.
So yeah, so only that's why I was saying 50% of reforming, 40% of reforming. So that energy that you are, the temperature that you are giving is only enough for, like, your 30% to 40% of higher hydrocarbon will be reformed to lower hydrocarbons.
Okay.
But
So in
your,
any of the case, not only in the pre-reforming,
okay.
generally we are talking about any equations where the temperature is being mentioned. So that is not going to give the complete reaction, right? So some certain amount of reactant is going to be there in the product.
No, I'm not getting your point fully actually. So
No,
suppose if I am saying the steam methane reforming and I am saying the temperature 850 degree.
yeah,
So the meaning of this, that you are having a reactor. So you need to maintain the reactor at this temperature.
yes, understood. Now my
Okay.
question is that the reactant is there in this steam reforming, like CH4, sorry,
CH
yeah, CH4 and
methane is
H2O.
CH4 is there. H2 is
CH4
there.
and
Yeah, right.
H2O. Yeah.
Okay.
So that is going to be the reactant, which
Yeah.
is going to be fit to the reactor. So
Okay.
if I give 850 degrees Celsius,
Mm-hmm.
whether this complete reactant is going to be changed as the product 100%?
Yeah. Okay. Yeah. So this is a good question. So it depend on some other parameter also. So the thing that this reaction, so you have temperature, okay, it's fine. So your temperature is promoting the reaction in forward direction, okay, but this reaction also require time to complete, na. So that your dimension of the reactor should be suitable, so that your so that this reaction have sufficient time to complete. Okay, so it depends on the flow rate. Suppose this reactor is, my reactor length is 1 meter, and I have calculated that 1 meter reactor, if I'm using the length of 1 meter and also the amount of catalyst. Okay, so I'm having a particular amount of catalyst, suppose some consider any amount. So this reactor I have calculated, it is sufficient for, if the flow rate of the methane is 1 meter cube per second. Okay, like 1 meter cube per second, and steam to carbon ratio is 3.0. Then if I consider, I compare the outlet gas, then I am getting 100% conversion. So basically the temperature is there. With this condition, I can get 100% conversion. So the whole reactant will be converted into product. Now, if I increase the velocity of input, I am making it 2 meter cube per second, then the output will not 100.
Yeah, it will drop.
It will drop. Why?
Because of high velocity.
Because
The rate
if
of
you are,
reaction drops.
yeah, the rate of reaction will come down. So maybe you then your, because your length is fixed 1 meter, so some amount of methane will not have enough time to complete the reaction. There is temperature is there, the steam is there, but they don't have enough time. So some molecule will leave directly, so that in this case maybe you will have only 70% of conversion. So it means that 30% of methane is unreacted, unreformed, that is coming directly out.
Yes.
Okay, so there are multiple factors in reforming. It is not only the temperature, it is not only the steam to carbon ratio.
Okay.
Okay, so there are multiple factors you have to consider whenever you want to design a reforming reactor.
Okay, got it. Okay.
Okay. Okay, so this is my email ID. So whenever you have any doubt, you can put an email to me. So now we have already taken the class of week 1. So if you have any doubt in your week 1 assignment, so you can email me after the due date only. Okay, so if due date is already crossed, then only I will be able to answer. Okay, so now we still have 10 minutes left, so we can discuss more about. Okay, so we can discuss. So you have any doubt about this thing, this process flow?
Just
Amit.
in the next system, you please try to look for that ortho and para hydrogen
Yeah,
difference.
sure. I will
That is
address
one
that.
point. And the second question, second point is that regarding the reaction, chemical reaction, what are the other courses are available?
The
Please just
kinetics, na you I think
yeah,
you were asking about the
kinetics.
reaction kinetics. So for the
Right.
kinetics, I am clear now. For the kinetics in this course, the kinetics will not be covered.
No, it's okay. But what are the other courses available? Just we want to know.
Okay,
About
for the other course, if I will get to know about any course, I will share with you. But it's better if you also look on the NPTEL website.
Okay.
So there will be some chemical engineering courses, so you can find a good course about reaction kinetics.
Okay.
Yeah. Any other general doubt?
Sir, what is the meaning of sintering?
Plasma reforming.
Yeah, Mihir. Yeah. Please, Mihir.
Sir, what is the meaning of sintering? Sintering process.
Okay, yeah, sintering. So sintering, I'm also don't know in detail about the sintering really. Anybody from chemical engineering background?
Sintering, it's kind of changing from its original shape, like converting into the powder form. So catalyst
Actually,
sintering.
sintering is just like a type of agglomeration. The particles fuse together to form an irregular shaped material. So that is basically called as sintering. For sintering, some binders or some element is been added to form that particle. Basically, sintering materials are used in blast furnace for making the iron and steel. So there they use the coal or some other constitution to make the sinter. In the reformer, sintering it means that the carbon, due to the free carbon, it fused together to form the sinter and chokes the reformer tube.
Yeah, thank you. It's good to know about sintering.
Yes,
Yeah.
Selva,
So
something about to say?
No, same thing I want to say. And one more thing, Amit, I just want to know about the pyrolysis process. So in the method of hydrogen production from coal, I saw the pyrolysis process. Could you please explain on this?
So the pyrolysis, basically, I think in this it is about we control the amount of air. So we control the amount of air and increase the temperature. So maybe in detail I will discuss in next class the pyrolysis. But it is like in the gasification, we are using biomass and we are burning it. But in the pyrolysis, so we are controlling the amount of air. So there will be also biochar in the output with the pyrolysis. So you can also use that biochar for other applications. You can have the syngas. So that is one part. So, but for detailed discussion, I can discuss in next class.
Yeah, it is. I can tell you something. It is, combustion in absence of oxygen or controlled oxygen and
Controlled,
gas.
yeah. We control the amount of air, yeah.
Okay. Okay, thank you.
And sintering also is a thermal process. Like we say annealing, we say combustion. That way, it is a sintering. Is again a thermal process wherein some like sintered materials are being created. So it is all about temperature range and the process where particles can be joined and sintered material can be created.
Yeah, nice, good to know. So this is the benefit of this live session. So we can interact with each other. We have a opportunity to like discuss more about some other topics also, and we are able to share our thoughts. So thank you for your time. So I hope you all will also join next time in next class.
Thank you.
Yeah.
Thank you.
So
Thank you.
just one
Amit.
question. Can you kindly tell when is the next class?
Yeah. So the next class will be on next Friday. So next Friday, same time, 6 to 8 p.m. So every Friday there will be a live session in which we will discuss the previous week's course content and we will go through some questions and discussion.
Okay, Amit, I want to say one thing. Yeah, you're really doing a good job here. So,
thank you.
Going for an open session and discussion, it really help us in knowing a lot of things. So thank
Yeah.
you very much.
Thank you. So because whenever we have discussion, so there are different points. So it's very good for me also because I am also getting to learn more things. Yeah. So it's a both way process. So it's good.
Yes. Okay. Thank you. Thank you all. Have a nice day.
Thank
Yeah.
you.
Thank you everyone for joining this
Thank
session.
you. Thank you all.
So yeah.
Thank you, sir.
Thank you. Thank you.
Thank you all. Thank you,
Thank you.
Amit.
Thank you. Thank you. So I'm
Now can we leave the
okay.
meeting?
Yeah, you can leave. Yeah, you can leave. No issue. Yeah.
I have one more question that we have another
Yeah.
scheduled meeting on 30th July.
So it will be on the next week.
Yeah, so the thing is that for a particular course, there will be more than one TA. So I am one of TA. So maybe there is one or two more TAs for this course. So like I am taking this class, so there will be another person who will be also taking the class. So it is for your suitability, so that if you are available on Friday, you can take mine class. If you are not available on this session, so maybe you can take another session. But in that session also, he or she will discuss the week one course content only, and that will be a live class.
Okay, okay.
Yeah.
Hello, Amit. Actually, I'm at work right now. I couldn't attend the whole session. Can we get the recorded session of this?
Yeah. So the NPTEL team will provide the recording and the PPT that I was using. So you will get both the PPT and the recording. So maybe in 2-3 days they will create a Google Drive link, and they will share that link with you. So on that link you will be able to find the PPT and videos for this session also and for other session also, because there will be more than one session. Okay, so maybe one of my colleague will be also taking a class, so you will also able to get the recording of that session.
Okay, thank you. Thank you.
This is Dilakshyan here. So yeah, same thing here. I was also not able to attend this class today, and I hope I will not be able to attend on every Fridays because we are already having some kind of a scheduled task. So if I attend on Tuesdays, I hope that will capture the lectures.
Yeah, sure. So if one session is on Friday and another will be on another day, so I think you are saying that Tuesday is there, so you can attend that class. And if you are not also available on Tuesday, then you can have access to the recordings.
Okay.
And
Fine, thank you.
if you still have doubts, you can email me.
Okay, that's good.
Yeah. Okay. Thank you, everyone. Any other doubt?
Sir, what about assignment if you miss?
So the assignment, each assignment is having some marks. So if you are not submitting on time, then you will not getting that marks. So at the end of the exam, there is some criteria for the passing the exam. So you need to fulfill that criteria. For that, I advise you to submit your assignments on time. Okay, guys. Thank you. Bye bye. Have a nice day.
Thank you, sir.